Hello everybody, I'm Jongmoo Lee with ETRI, and I'll talk about programmable quantum circuits and silicon photonic chip. And here I'm showing the chips. This chip was fabricated last year and packaged at the end of the last year like this, and then analyzed in this winter. And the other chip is fabricated only 2 or 3 months ago, and then I packaged this chip like this way. You can see the difference. There are more electrodes than before, about 80 electric point for the control of the program of this circuit. And I changed the contact point from this is the pin to the this flexible cable for more electric control. So this shows how to use the photonics integrated structure for the quantum circuit or the quantum computer. We use 2 array of waveguides. That's one as for 0 and the other one for 1. And then by using the margin interferometer, we can make the arbitrary gate of a single qubit. We can rotate on the surface of the black sphere to any point by using this margin interferometer. And we can also make an entangled 2-qubit state by forming the 2 photon pair source and then crossing their way like this way, one photon pair generated to 0, 0 position, and the other one to 1, 1 position. And we don't know from which pair source the photon to come, but the resulting the qubit is the 0, 0 or 1, 1. So we make the entangled pass qubit using this structure, and then we call it as a fusion operator. And we can also make a control G and control NOT gate by combination of these margin interferometers, and also the more complicated quantum circuits like this way. And this is the current state of the quantum technology. There are several technologies applied for the development of a quantum computer. Most popular one is a superconducting qubit, but recently the silicon photonic is attracting the people with the vision of the preparing the large amount of a qubit by fusion operation of the photons. So we are also working on this silicon photonics qubit toward the large cluster state of photons. This shows the measurement-based quantum computing, or the called in another way, the fusion-based quantum computing. For the measurement-based quantum computing, we need the large scale of the entangled qubit. And if we can prepare the large amount of entangled photon cluster, then we can solve any quantum program, such as for an example, the Grover's algorithm could be solved by the 4-photon entangled structure. We can use the 2 entangled photon as an oracle and the other 2 entangled photon as a diffuser. So this kind of 4-photon entanglement is equivalent to the solution for the Grover's algorithm. So it's not our figure, but the PsiQuantum's figure that they are trying to build a large amount of entangled photon cluster by using optical fiber as a quantum memory. and then entangling the photons on the surface and also on the axis of the time. So for that, we need the low loss and fast switching and also fusion operators. And recent result by the Janadu is a little different from the psi-quantum's approach that they are using multiphoton state, and then this result based on the bulk optical switches. But anyway, they use the fibers as a quantum memory, and with the switching, they made the three-dimensional quantum cluster, and they used it for the boson sampling. So this shows that how we can make the large dimension of the quantum state with photons. So quantum computer can be made with photon like this way. On silicon photonic IC, we can make a photon pair sources and programmable linear optical quantum circuit. And even we tried to integrate the single photon detector on the silicon photonic IC. And these can be controlled by electric IC. And also the fiber is connected to the silicon photonic IC for a short time memory. This is about the photon pair generation. And this shows how to increase the entanglement of the photons by fusion operation. Crossing the two, getting the two photon entangled states and four photon entangled states. And then we can also use the single photons or the heralded single photons to generate the entangled states like this way. The two photon and four photon entangled states can be prepared by this fusion operation. And this shows how to increase the entanglement. And if we can make these four photon entangled states, that could be a building block for the fused entangled states. By more fusion with the other the four photon entanglements, it can be like a Lego. We can build a three-dimensional entangled states in space and also by using time axis. So we need to develop such things. And one problem is that current silicon photonics technology has a problem in some parts. There are many ways of switching method using silicon or silicon nitride or lithium niobate, but all of them has already problems, such as for thermal optics, it has a problem in speed, and the carrier modulation by carrier density has a problem of the loss, and also lithium niobate has a problem of the CMOS compatibility. And to solve this, there is an effort to apply new material called as BTO that has a very big nonlinear optical property. So and people are developing the BTO enhanced silicon photonics for the purpose of this quantum computing development. This shows the Hongou-Mandel effect, which is very interesting effect with the photons. That two photons goes together when it passes the beam splitter. And on the silicon photonic entry circuit, I can experiment the Hongou-Mandel interferometer by using margin interferometer. By changing the phase of the margin in the interferometer, it can be a beam splitter or it can just see a passing or the crossing. So if it works as a beam splitter, there's no coincidence, and if it passes the single photon, then there is this coincidence of the photons. So it can the transfer can be the coincidence transfer can be like a cosine square function. And with this, we can measure the visibility of the photons, and also can make the two-photon gate of control G or control lot gate. And I fabricated some chips, and some of them was used for the CNAP gate operation 2 years ago, and the recent chip is used for the on-chip Hong-Mann visibility, and we got the measure result of 98.9% visibility with the on-chip Hong-Mann interferometer. And the other chip is recently packaged from our experiment. And this is the on-chip Hong-Mann interferometer experiment. The photon pair generated through the silicon waveguide, and we control the resonance of the ring, also control the phase of the margin interferometer, and we can characterize many things with the circuit. And one of them is the Hong-Mann interference of the two photons. And we got the 80% Hong-Mann visibility with the photon pairs from the ring, and the 98.9% visibility with the photons from just set waveguides. It's a little difficult why the ring has the low visibility was analyzed in other reports. That it's a complicated story, but anyway, there's some effort on increasing the visibility even with the ring. Anyway, we are using both the ring and straight waveguide for the high repetition. In case when we need high repetition, we use ring, and when we need the high visibility, we use the straight waveguide. And this is my recent chip. I finished the package of this chip, but I still need to some electronics job for the control, and then I have to make the computer program to control this chip. And anyway, this chip was designed for the experiments such as tomography and Bell state generation and the on-chip teleportation, and also fusion up to 4 photons. I mean, there is a fusion operation here for the 4 photon to generate the 4 photon entangled state. And this is my recent design to increase the capacity of photons to the 8 photon state. So this design includes the fusion operation up to 8, but it doesn't mean that I mean that the fusion up to 8 photon requires the photon coincidence of 8 photons, and it will not be easy for the measurement of the coincidence of 8 photons. But anyway, this design is targeting for the fusion up to 8, and then I have to see how it works well for the 8 photon entanglement. And this part is my design for Grover's algorithm for 2 photon qubit, but after the design, I found that there is some mistake. That it means that it's more complicated than my first thought. That for testing Grover's algorithm, I found that I need to use more than 4 photons or even up to 8 photons for 2 qubit Grover algorithm. So I have to revise this design for the next design. So in our recent project, which is led by KAIST, and then with consortium with KAIST ETRI and Sungkyunkwan University, and we are developing each component for the required for the fit for the quantum computing. This is a 2-year project, and we are developing each component, the SNSPD, and the ASIC electronic IC for the control, and also the switch ICs. And we hope we can show the basic idea of the fit for the quantum computing with by the connection of these components, and then our future will be we'll try to integrate all of them in a circuit. That's my conclusion of this talk. Thank you very much.
Thank you, Dr. Lee, for the interesting talk. We have time for a couple of questions. Okay, then let me ask you, can you have a question? No? Okay. So can you shortly summarize what your photonic device distinguishes from others? Maybe I missed that one.
From others? Yeah, there's not much difference from as we are watching the best players such as PsiQuantum, how they are doing, and then we are trying to develop our own components similar to their scheme. Even the PsiQuantum didn't show any experimental result yet for the fit for the quantum computing. So we are trying to develop our own component and try to show the fit for the quantum computing with our components. And in detail, there are some variations, such as in my design, I'm using both of the ring resonator and the straight waveguide for the photon pair generation, and I can select which to use for my purpose. Such minor things included in our design.
Okay, thank you. So one more question. So we have 2 more. So one behind. Yeah. So first and then next.
Thank you for your talk. Can you give some idea of how fast the optical switch, the photonic switch, operates? What's the switch time and slew rate and so on? Just technical questions.
Yes, good question. As I said, I think we need the speed more faster than nanosecond for the fast information process for the quantum computing. But now I'm using the sum of the switches, and it's not so fast. So we have to develop other type of photonic switch for the fit for the quantum computing.
Okay. So to your right, yeah, there's.
My question is that what is the polarization state? And the other question is the maximum insertion loss from the input to final output. Maximum insertion loss.
Yeah. Let me show with my experiment scheme. Here, we fix the polarization. If we can use the polarization also for the qubit, we can double the amount of qubits. But for now, we use the fixed polarization, but we use only the pairs as the qubit. And then optical loss for now, after the generation of the photon pair, within this chip, the optical loss is very little, so we can neglect the loss inside the chip. But the optical loss is most of the loss is for the out of the chip. and there's the bandpass filter and the fiber connection. Then most of the optical losses are here. But for the quantum interference within the chip, because there is no negligible optical losses, so we can get a very nice Hong-Mandel visibility.